Welcome to the fourth part of Module 6C 203 Fluid Mechanics 1. So in this video we'll be discussing the remaining three types of problems, type 4, type 5 and type 6. So first type 4 problem. In this type of problem, velocity profile, that is U by U equation, will not be given. So in such a case, we need to use the Blasius equations. We have already discussed about Blasius equations in the previous videos. So as we know, Blasius has given two sets of equations. One for laminar boundary layer and another set of equations for turbulent boundary layer. So when you get a type 4 problem, you need to first identify whether it is laminar boundary layer or turbulent boundary layer. How to find out that? You have to find out the Reynolds number. So first step is to find out the Reynolds number and compare the value in order to find out whether it is laminar or turbulent. So these are the equations. These are the equations for laminar boundary layer. It is a laminar boundary layer if the Reynolds number is less than 500 raised to 5, and these are the equations. And if Reynolds number is in this range, then it is turbulent boundary layer. You can choose the equations accordingly. Okay. So we'll see an example. A plate of 600 mm length and 400 mm wide is immersed in a fluid of specific gravity 0.9 and kinematic viscosity nu is equal to 10 raised to minus 4 meter square per second. The fluid is moving with the velocity of 6 meter per second. Determine first one, boundary layer thickness. Boundary layer thickness is nothing but your delta. Then second one, shear stress at the end of the plate. So that is tau naught. And third one, drag phase on one side of the plate. Yeah, in the equation, if you apply the equation, you'll be getting the drag force on one side of the plate only. If in any question total drag force is asked, then you have to multiply FD into 2. Then only you will be getting the total drag force on the plate. Okay, we have discussed this in the previous video. So we'll write down the given data. Length of the plate L is equal to 600 mm. Width of the plate B is equal to 400 mm. Specific gravity of the fluid S is equal to 0.9. Density can be found out by multiplying specific gravity with 1000. So 0.9 into 1000, that is 900 kg per meter cube. The velocity of fluid is given 6 meter per second. Kinematic viscosity nu is given. Then here U by U value is not given, isn't it? So we can apply Blasius solutions for finding the unknowns. So first step is to find out the Reynolds number. Here Reynolds number is found out, and we'll compare this value with the standard values. So here we can see that the obtained value is less than 5 into 10 raised to 5. What is the meaning of that? That means the boundary layer is laminar. So we can choose the equations given by Blasius for laminar boundary layer. So this REL value, Reynolds number value, is less than 5 into 10 raised to 5. Hence the boundary layer is laminar over the entire length of the plate. So this is the delta equation given by Blasius for laminar boundary layer. Here X is equal to L. See, in the equation, what is X? X is the length of the section that we are considering from the leading edge. So, we are finding delta at the end point of the plate. So, at the end point, the distance from the end point to the leading edge is the total length of the plate. So, here instead of X, we can apply the value of L, total length of the plate. So when you apply, you'll be getting delta as 15.5 mm. Now we can find out tau naught using that equation. We'll be getting the value at 56.6 Newton per meter square, and then we can find out CD for finding FD. Then you can find out FD also. Okay, so this is the this is how you do type 4 problems. See, one point that I need to tell right now is that this equation is applied when the boundary layer is starting from the leading edge, or we can apply this formula when we have the thickness of the boundary layer is equal to 0 at the start point. Okay. What I meant is that if you have two sections, section 1 and section 2, okay, 1, 2, okay. If in any question we are asked to find out the drag force only for this particular portion, we won't be able to directly apply this formula, okay. But if the drag force for the entire plate is asked, we can apply this formula, okay. Now we'll do another problem. Water is flowing over a thin smooth plate of length 4 meters and width 2 meters at a velocity of 1 meter per second. If the boundary layer flow changes from laminar to turbulent at Reynolds number 510⁵, find first one, the distance from the leading edge up to which boundary layer is laminar. So that means, so you have the plate. For a particular section, the boundary layer is laminar. Then it changes from laminar to turbulent. So beyond this point, the boundary layer is turbulent. Okay, so you have to find out the distance from the leading edge. This is the leading edge. So from the leading edge up to which distance the boundary layer is laminar. So you need to find out this distance. Okay. Second one, the thickness of the boundary layer at the transition point. So here you have the transition point. Here you have the transition point. So at this section, what is the thickness of the boundary layer? Then third one, you have to find out the drag force on one side of the plate. One side of the plate is asked, so you can directly apply the formulas given. Viscosity is given as mu is equal to 9.81 into 10 raised to minus 4 Newton second per meter square. Okay. Now we'll write down the given data. Length of the plate is given L is equal to 4 meters. Width of the plate is also given 2 meters. Velocity of flow is given as 1 meter per second. Reynolds number for boundary laminar boundary layer is given as 5 into 10 raised to 5. We all know this value. Viscosity is also given for water. Okay. And in this particular question, it is clearly mentioned in the question itself that we have both laminar boundary layer and turbulent boundary layer. Up to a section, it is laminar. Beyond that section, it is turbulent. Okay. So first we'll find out what is the distance from the leading edge up to which the boundary layer is laminar. So at this particular section, what will be the value of Reynolds number? At this section, the Reynolds number will be 5 into 10 raised to 5. Okay. So we'll just take this distance as x from the leading edge to this section. Let this distance be x. So let the distance from leading edge up to which laminar boundary layer exists be small x. So we can take the value of Reynolds number as 5 into 10 raised to 5, and we'll be substituting RE value in the equation of Reynolds number. We know that Reynolds number REL is equal to rho u x by nu. Here x can be found out from this equation. Okay, all other values are known. The only unknown is x. See, I'll write the equation over here. Rex is equal to rho u x by mu. Okay, so in this equation we'll be substituting the value of the Reynolds number, then rho value will be substituted, u value will be substituted, mu value will also be substituted. So we'll be getting the value of x, the distance. Okay, so x is obtained as 0.49 meters. So at a distance 490 mm from the leading edge, you have the transition point. So before that transition point, the boundary layer is laminar. Beyond that point, it is turbulent. Okay. So here you have the figure. We got the value as 490 mm, that is 0.49. So at F, you have the transition point. From E to F, the distance is 0.49, and beyond that, you have turbulent boundary layer. So first part of the question is over. Now for the second part, what is the second part? The thickness of the boundary layer at the transition point. So at this point, at the transition point, the flow is laminar. Okay, so we can use the equations for laminar boundary layer. The equation for delta from laminar boundary layer is 4.91 into x by root Rex. Rex value at this particular point is 5 into 10 raised to 5. So substitute the values and you will be getting the value of delta. Delta value is obtained as 3.4 mm. So the thickness of the boundary layer at F is equal to 3.4 mm. Okay, so first part of the question is over. Second part of the question is also over. Now, the third part of the question is to find out the drag force on one side of the plate. Okay, so the next part of the question is to find out the drag force on one side of the plate. Here, I have mentioned earlier that we can apply the equation directly only if the boundary layer is starting from thickness 0. Okay, here the problem is up to F. In this region, the boundary layer is laminar, and beyond this, the boundary layer is turbulent. So we need to add these two in order to get the total drag force. In this region, E to F, you have from E to F you have laminar boundary layer, and so using the equation you can find out the drag force for laminar boundary layer, and we need to find out the drag force for turbulent boundary layer for the section FG. For the section FG, we cannot apply the formula directly. That is the problem in this case. Okay. Anyway, we'll find out. First, we can directly find out the drag force in region EF because it is starting from thickness 0. Okay. So, you can directly get that. So, as I told you, drag force is equal to drag force due to laminar boundary layer plus drag force due to turbulent boundary layer. There is some problem in finding out this, but this thing we can easily find out. So we'll find out the drag force due to laminar boundary layer. You can easily use this equation. Just find out the area. Yeah, when you take the area, see, let me draw the plan of this plate. When you look from the top view will be like this. Okay, so till this section you have laminar boundary layer. So we are taking this area for finding laminar boundary layer drag force. Okay, so this distance is 0.49 and the width is 2 meters. So what will be the area? Area will be 2 into 0.49. So that area is written over here. Okay, so here A value is 2 into 0.49. You can substitute the values and you'll be getting the force, drag force due to laminar boundary layer, that is from E to F. So this part is over. Okay, now we'll move on to this part. Now here what we do is we'll assume that for the entire length EG we have turbulent boundary layer. Okay, we'll make such an assumption, and what we do is we'll first find out the drag force due to turbulent boundary layer from E to G for the entire length. Okay, we'll take that value. Then what we do is we'll find out what is the drag force due to turbulent flow from E to F. Okay, in this portion, if it was turbulent boundary layer, then what will be the drag force? That value will be found out. Then we'll subtract this value from this value in order to get the value for FG. Hope you understood what we are doing. We are assuming that for the entire length it is turbulent boundary layer. Then we'll find out the drag force for EG. Okay. Then we'll find out the drag force for EF, and actually what is required is the drag force for Fg. So now how to find out the drag force for Fg? You can just take the difference of these two. Eg minus Ef will give you the drag force for Fg. Okay, so we'll first find out the force for Eg, turbulent drag force for Eg. So Feg, here it is E. Feg is equal to this equation. You can apply this equation because here the the boundary layer is starting from thickness 0. So you can apply this equation. When you apply, here the equations for turbulent boundary layer is used. Okay, we are assuming that it is turbulent boundary layer. So these are the equations given by Blasius, and here one point to be noted is that the area is 4 into 2. So as I explained in the previous slide, if you take the plan, the total length is 4, the width is 2. Okay, so when you are considering the entire area, it will be 2 into 4. So that is substituted over here. Okay, 4 into 2. So this value 13.72 is the drag force from E to G. Okay, now we'll find out the drag force from E to F. So drag force from E to F. Here what will be the area? Here F is over here. So we'll be taking this area only. That means 2 into 0.49. See here 2 into 0.549 is taken as the area. And the equation used is for turbulent boundary layer. So when you do that, you'll be getting the force for EF portion as 2.557 Newton. Okay. So how to find out the force for Fg? You can take the difference. So drag force due to turbulent boundary layer from F to G is given by subtracting this value from this value. So drag force for Fg is given by 11.163. Okay, so this is for Fg. Now, how to find out the total drag force? We have already found out what is the laminar drag force for length EF in the previous slide. So, that plus this value 11.163 will give you the total drag force on the plate. Okay, so drag force due to laminar boundary layer up to F plus drag force due to turbulent boundary layer from F to G. So the final answer will be 12.083 Newton. Okay, so this is a very interesting question. Now we'll move on to the next type of problem. So in this type, we have to say whether separation of flow has taken place or not. Okay, velocity profile will be given in this case. U by U value will be given in this case. So based on U by U value, you have to say whether it is separated or not. So these are the conditions you need to study these conditions. If dou U by dou Y at Y is equal to 0, you have to find out this value first. Okay, dou U by dou Y at Y is equal to 0. If this value is negative, then the flow has separated from boundary. Boundary layer separation has occurred. Then, if this value is equal to 0, then the flow is on the verge of separation. It is just about to separate. Then, if this value is positive, then the flow will not separate and will remain attached to the boundary. So, these are the three conditions. This is a very simple type of problem. I'll just show you an example. Okay, here, the following velocity profile. We have the velocity profile with us. Determine whether the flow has separated or not, or on the verge of separation, or will attach with the surface. We have to just tell whether the flow has separated or is at the verge of separation or will it attach to the surface? Okay, so as discussed in the previous slide, we have to first find out, u by u value is given. We have to find out dou u by dou y. For that, from this equation, you can write the expression for u. Okay, then differentiate the equation of u with y. Differentiating with y, you can find out dou u by dou y. So this is the value of dou u by dou y. Then substitute the value of y as 0. So that you will be getting the value dou u by dou y at y is equal to 0. So this is what you got for dou u by dou y at y is equal to 0. Is the value positive? Yes, the value is positive. That means the flow will not separate or it will remain attached to the surface. So based on the conditions mentioned in the previous slide, you can say whether it is separated or it is at the verge of separation or it will attach to the surface or not. Okay, so this is type 5. Now we have one more type, the last one. It is to find out the drag force, lift force and the total force, direction of total force and the power exerted on the body by the fluid. Okay, so we have studied all these equations in the previous videos. So total force Fr is equal to root of Ft square plus Fl square and theta is equal to tan inverse Fl by Ft. The power exerted by the body on the fluid or vice versa can be found out by multiplying the force in the direction of motion. Force in the direction of motion is nothing but the drag force Fd. Fd into the velocity, free stream velocity. Okay. So we'll just consider a few problems. Experiments were conducted in a wind tunnel with a wind speed of 50 km per hour on a flat plate of size 2 meters long and 1 meter wide. Okay. The density of air is 1.15 kg per meter cube. The coefficients of lift and drag are given. Determine the lift force, that is Fl is to be found out. Determine the drag force, that means Fd is to be found out. The resultant force Fr is to be found out. The direction of resultant force, that is theta, is to be found out. The power exerted by air on the plate is also found out. So these are the things to be found out. It's a very easy question. These are the given data. Area of the plate is given. Velocity is given in kilometer per hour. We have to convert that into meter per second. Density of air is given. CD and CL values are also given. So it is very easy. Lift force and drag force can be found out using direct formula. These are the formulas. So you will be getting the value of FL and FT. Then how to find out the resultant force? Take the resultant of FL and FT. So you will be getting the Fr value. Then direction is given by tan theta is equal to Fl by Ft. So theta is equal to tan inverse phi. You will be getting the direction of resultant force also. Then power is equal to force in the direction of motion into velocity. Force in the direction of motion is nothing but your drag force. Drag force is always in the direction of motion. Okay. So you can refer to the previous videos for that. So Fd into U, you will be getting the power in watts. Okay, if you substitute the values in a Newton and meter per second, you will be getting the power in watts. So this is how you do a sample problem. So with that, we have one more problem. A kite 0.8 meter by 0.8 meter weighing 0.4 kilogram force, that is 3.924 Newton, assumes an angle of 12 degree to the horizontal. The string attached to the kite makes an angle of 45 degree to the horizontal. The pull on the string is 2.5 kgf, that is 24.525 Newton. When the wind is flowing at a speed of 30 km per hour. Find the corresponding coefficient of drag and lift. Density of air is given as 1.2 0.25 kg per meter cube. Okay, so in this question we have a kite. And it is not horizontal or vertical. It is inclined to the flow of air, and there is a string attached to the kite also. Okay, so in this question we need to find out the coefficient of drag and lift. CD and CL have to be found out. All the forces acting on the kites is given. All the forces are given, and we know that the horizontal component of all the forces will be your force FD, and the vertical components, if you take the sum of all the vertical components, that will be your lift force or FL. So FL value and FD value can be found out. From that value we can find out CD and CL. Okay, we'll write down the given data. Area of the kite is given, weight of the kite is given, angle made by kite with horizontal is given, angle made by string with horizontal is given, pull on the string is given, it is given as 2.5 kgf. We can convert that into Newton by multiplying with G, 9.81. Then speed of the wind is given in kilometer per hour, that can be converted to meter per second. Density of air is also given. So as I told you, first we'll find out FL and FD. FD is in the direction of the motion and FL is perpendicular to the direction of motion of the wind. Okay, so this is the figure. The forces which are acting on the kite is shown in bold lines. So we have W and P, they are the forces. So just take the horizontal and vertical components. In the horizontal component will be your FD and vertical component will be FL. So FD is the force exerted by wind in the direction of motion. So W is acting in vertical direction. So it won't be having any component in the horizontal direction. So you can just omit this W when you consider FD. So what is the component of P in the horizontal direction? It is P cos 45. This angle is 45. So P cos 45 is the component in horizontal direction. So FD will be P cos 45, that is 17.34. We got the value of FD. Now we'll find out the value of FL. FL is the take the sum of all forces in the y direction or in the vertical direction. So in the vertical direction you have the weight W and the component of P. So W plus P sine theta. Here this is 45. So horizontal component will be P cos 45 and the vertical component will be P sine 45. So P sine 45 and W both will be in the downward direction. So we can actually add those two. Okay. So P sine 45 plus W will give you your lift force, that is FL. So FL is obtained as 21.264 Newton. We got the value of FD and FL, and now we can easily find out the value of CD and CL. So this is the equation. In this equation all the values are known except for CD. You can find out CD, and CD is obtained as 0.624. And now in coefficient for CL, in this equation all the values are known except for CL, and CL can be found out. It is found out to be 0.765. So this is how you do problems, type 6 problems. Okay. So with that we wind up module 6. I hope everything is clear. Thank you. All the best.